Welcome. In this video, I'll be determining whether this infinite series here converges or diverges, and I'll do so using the comparison test, also known as the direct comparison test. Now, anyone who's watched a couple of my videos already notices that when I begin these, my strategy is always to start with some comparison. So I'm going to say for n greater than or equal to 1, that is for n values starting here. And then I usually want to look at the reciprocal of this. So I'm going to begin with just the denominator here, which is n times n plus 1. Well, this equals n squared plus n. And clearly, this always has to be greater than n squared. If you don't believe this and don't see this, pause the video and try in values of n equals 1, n equals 2, and so on, and informally prove this inequality to yourself. All right, now that you've proved this inequality to yourself, let's continue. So we know for values of n beginning at 1 and getting larger, this inequality holds. So we can also say, hence, n squared plus n divided by 5 must be greater than n squared divided by 5. Again, I've changed nothing. I just divided both sides by 5. And now what do I have here? Well, I have the reciprocal of my series. So it follows that 5 over n squared plus n is less than 5 over n squared. Now this leads me to the series I'll be comparing to. So let's look at this. The series from n equals 1, that is the sum from n equals 1 to infinity of 5 over n squared. Well, this is a p-series with p equals 2, which is greater than 1, so this series converges. Since 5 divided by n squared is always larger than 5 divided by n squared plus n, it follows that this series, especially since this one converges, also converges, and that's by the direct comparison test. And here is now my conclusion, which references the series that we compared to, references that it converges, and references the comparison test, and then states that our series converges.